So this is the solution for quiz 8, which is, of course, the last quiz of the semester. So let me go over how you do these problems. And, of course, my numbers are on the first page of the printout. Okay, so the first few questions were related to momentum. The first couple were inelastic collisions. So for inelastic collisions, the momentum that each of them have before they collide, the two masses that is m1v1i plus m2v2i. This is the momentum of mass 1 before the collision. This is the momentum of mass 2 before the collision. And of course, for an elastic collision, they stick together and they move at one common velocity vf. So they're stuck together, so they behave like one mass, which is m1 plus m2 after they collide, moving at some velocity vf. So this is the final momentum after they collide, which is written on your equation sheet, and that's basically how inelastic collisions basically always work. So for this problem, you knew everything but v1i. So you basically just rearrange the equation. You subtract m2v2i from both sides. You divide by m1, and that gives you v1i, and you plug in the numbers, and you get positive 18.40, which means mass 1 was moving at 18.40 meters per second in the positive x direction. So once again, you should know how to do inelastic collisions, how to find any of the velocities or masses using the conservation of momentum for inelastic collisions. So for number 2, you do the same thing you did for number 1 at first, exactly the same thing, and you find how fast mass 1 was going once again before they collide. And then when the question was, what is the average force on the 2 kilogram mass? So the average force on the 2 kilogram mass is the change in momentum of the 2 kilogram mass, which I call mass 1, by the way. So it's m1vf, so v1f, remember, and v2f are both equal to vf because they're stuck together, right? So basically, both mass 1 and mass 2 after the collision move at the same velocity, which is vf, right? So this is v1f. So in other words, what I'm trying to say is the momentum of the final momentum of mass 1 is m1 v1f, but v1f is equal to vf for inelastic collisions. And then minus the initial momentum for mass 1 before the collision, divided by the time it takes to collide. I factor out mass 1, or the 2 kilogram mass, and I plugged in the velocities carefully. Remember, velocities can be positive or negative, so you got to be careful. But vf was positive and v1i was positive, so they're both positive. So it's just basically the subtraction of those two numbers, and you get negative 700 newtons, but the magnitude is 700 newtons. In other words, this is 700 newtons in the negative x direction, but I didn't care about the direction, I just cared about the amount of the force. So it's just 700 newtons. You could also get it, by the way, by just finding the force on mass 2, which was 7 kilograms. Let me show you here. All right, so it'd be 7 kilograms times VF, which was 7, minus the initial velocity of mass 2, which is 7, so it's 14, divided by, what was it, 0.14. So that would be 7 times 14 divided by 0.14, sorry, which is 700 newtons, right? Once again, that's because the average force on each mass is the same, just with the opposite sign, meaning they're in opposite direction. So the other way you could have done it is just figured out the average force on the second mass, and you didn't really even have to solve for v1i if you did that. So I did it the hard way, but there was actually an easier way to do it by finding the average force on mass 2. But nonetheless, either way you do it, that's the answer. So 3, you have to find the kinetic energy loss. So you have to first figure out once again how fast mass 1 was going before the collision, so you can figure out the kinetic energy of mass 1 before the collision. So we do the same thing that we did in 1. And then the total kinetic energy initially is the kinetic energy of mass 1 before they collide, which is 1/2 m1 v1i squared, which is 1/2 of 5 times 20.4 squared, whatever that gives you. That's just the kinetic energy of mass 1 before the collision. And then mass 2 has some kinetic energy before they collide, which is 1/2 m2v2i squared, which is this for mass 2. So I could actually do this in my head because it's 2 squared, which is 4 times 9, which is 36, divided by 2, which is 18. So basically mass 2 has 18 joules of kinetic energy before the collision, and mass 1 has a lot of kinetic energy before the collision, but you add them up. That gives you the total kinetic energy that they have before they collide. Then after they collide, it's basically like a 5 kilogram and a 9 kilogram mass stuck together. So a 14 kilogram mass, that's 4 plus 9, moving at the final velocity of 6 meters per second, which is what I did here. So that has some kinetic energy of basically 1/2 of 14 times 36, which is 252 joules. So once again, you should know that in an inelastic collision, you lose kinetic energy. In this case, we go from this to that. So how much we lose is this, but in reality, I'm asking for how much is lost, which is 806.40 joules. Okay, so for 4 is a perfectly elastic collision, and in order to conserve kinetic energy, remember for perfectly elastic collisions, these two kinetic energy should be the same number, right, for perfectly elastic collisions. So you didn't know the masses, but the point is you don't need to know the masses, because for perfectly elastic collisions, to make sure the total initial kinetic energy is equal to the total final kinetic energy of this other equation you can use for perfectly elastic collisions, that v1i plus v1f is equal to v2i plus v2f. So you knew 3 of these velocities, but not the 4th one, so you just solve for the 4th one. It's pretty straightforward. You didn't know the velocity of the second mass, the final velocity of the second mass. So all you do is subtract v2i from both sides. You got to be a little bit careful because v1i was in the positive x direction, but v1f was in the negative x direction, so that's a negative velocity. And also, you subtract v2i, but v2i was also going in the negative x direction. The second mass was going in the negative x direction, and the final velocity of the first mass was going in the negative x. So you have to be careful because it's like 3.2 minus 6 plus 5.4 when you take into account all your negatives properly. And for me, I got negative 0.40 meters per second, meaning that mass 2 is going at 0.40 meters per second in the negative x direction. So 5 is also a perfectly elastic collision. I gave you, by the way, the easiest perfectly elastic collisions you can do. Usually, in a perfectly elastic collision, you have to use conservation of momentum and this equation to find the final velocities of both masses, or 2 velocities. But this, I set up 4, so you only need to use this equation, which isn't too bad for perfectly elastic collisions. And then for number 5, I asked the question in a way where you don't really have to solve for that much as well. Because I gave you the kinetic energy of one mass before they collide, the kinetic energy of another mass before they collide. So before they collide, you know how much total kinetic energy they have. They just add them up. And then I gave you the kinetic energy of one mass after the collision, which is 29 joules, but I didn't give you the kinetic energy of the other one. But the point is, for a perfectly elastic collision, you should know it for the test, that the total kinetic energy before should equal what's after. So this is before, this is after. You set them equal to one another, and you can just solve for the kinetic energy that you didn't know. So that was, a pretty straightforward. I don't know why that took forever to. Anyhow, it's just about the easiest perfectly elastic collision questions I could possibly ask. In other words, if they're typically have to solve 2 equations for 2 unknowns for perfectly elastic collisions, but I set 4 and 5 up so you didn't have to do that. So I thought they were pretty straightforward. 6, you have to use a constant angular acceleration equation. So now we're moving from inelastic, from momentum to rotation. So you use this equation because you knew omega f, you know omega I, the initial and the final angular velocity. You knew the angular acceleration, and you're trying to find something related to angle or revolutions. Revolutions is always an angle thing. So I solved this equation for delta theta. I subtracted omega I squared first, divided by 2 alpha. You got to remember that things that are counterclockwise are positive, things that are clockwise are negative. So alpha was negative. So it's going to, cause the thing to slow down. And so I get 136 radians. And then you have to convert to revolutions. So one revolution is 2 pi radians. So you just divide by 2 pi. And that gives you how many revolutions. All right, that's weird. So 7 was what is the rotational kinetic energy that something has. So you first have to figure out how fast it's spinning, because how fast it's spinning is related to how much kinetic energy, rotational kinetic energy it has. So you use this equation to figure out how fast it's spinning over 0.67 seconds, because we know the time. We know the angular acceleration is once again negative because it's clockwise. And you know the initial omega. So after 0.67 seconds, it's 26.32 radians per second. That's how fast it's spinning. Still counterclockwise. And then you just plug that into the rotational kinetic energy equation, which is 1/2 I omega squared, and I is cmr squared. So I give you the c value of the mass and the radius. And now you know how fast it's spinning, and you just plug it in. That gives you the rotational kinetic energy. Okay, I don't know why this is acting weird. Okay, so 8 and 9 were moments of inertia questions related to moments of inertia for point masses. So you should know that if you want to figure out the moment of inertia about the x-axis for a bunch of point masses, masses on the x-axis don't contribute because they're on the x-axis. The distance to them from the point mass to the x-axis is 0. So it's only the ones on the y-axis which matter. So both of these were the masses on the y-axis. So it's the mass times the distance to the y-axis, which is the y value. The y value plus the other mass times its y value. And that gives you the moment of inertia about the x-axis. All right. So for 9, it was asking about the y-axis. So the masses that are on the y-axis don't contribute. It's just, for this one, it was the mass on the x-axis times the its x-coordinate, basically, which is the distance to the y-axis. So that gives you the moment of inertia, which is important to know. But I'm asking for the rotational kinetic energy, which is 1/2 the moment of inertia times how fast it's spinning about the y-axis squared. So that gives you the rotational kinetic energy about the y-axis. 10, I don't know why I said 5, but 10 was pretty straightforward. If it's rolling without slipping, you have this equation that VCM is equal to R omega, so how fast it's moving is equal to its radius times how fast it's spinning, and that's pretty straightforward. So 10 was basically a gimme. 11, you first had to figure, there's a hint, you first had to figure out how fast it's moving at the top, so you do what you did in number 10. You take how fast it's spinning times its radius, and that gives you how fast it's moving at the top, which for me is 11 meters per second. Then you're going to do conservation of energy, calling y equals 0 at the bottom to find the potential energy at the top. Of course, at the bottom, the potential energy is 0 because you're calling it y equals 0. So the potential energy at the top is mgh, plus it has total kinetic energy because it's rolling and spinning of 1/2 mvcmi squared 1 plus times 1 plus c. The final energy is just total kinetic energy because we called y equals 0 at the bottom, which is this. And like I said, if it's just rolling and no other forces acting on it, normal force does no work, and you don't factor in static friction to energy, only kinetic friction, but this is static friction to make it roll without slipping. So EI and EF are the same thing. The mass cancels out because there's the mass everywhere. And then I just solve for VCMF squared, as I did in the homework, and as I do here again. I multiply by 2, everything by 2 to get rid of the 1/2. That makes this 2GH. That gets rid of that 2. So the 2 is gone. Then I divide by 1 plus C. So now this is 2GH over 1 plus C. That gets rid of that 1 plus C. So you're just left with VCMI squared plus GH over 1 plus C. And then you plug in, take the square root, and then you plug in the numbers, and that's how fast it's spinning at the bottom. So yeah, like I said in the homework solution, you need to know how to do total kinetic energy, how to figure out how fast something is moving, if it's rolling without slipping, how fast it's spinning if it's rolling without slipping. You need to know moment of inertia, rotational kinetic energy, and how to use the constant angular acceleration equations too. The rest of the quiz is now focused on torque. So 12, 13, and 14 are cases where the torque isn't zero, so it's rotating about the center. So what I did here is I drew the lines of action. This is for F1, the line of action here. So the moment arm from F1 is, I don't know what's going on with my cursor, right? It goes from the axis to the line of action perpendicular to it. So the moment arm for F1 is equal to R, and F1 makes this thing rotate counterclockwise about the center. So it's a positive torque, a positive F1 times R. The second torque, this is its line of action here, or the second force. The moment arm is from the axis to the line of action here. So L2 is half the radius, because that's what I told you. And this force makes it rotate clockwise, so it's negative. It's minus F2 times L2, or minus F2R over 2. And F3 goes, the line of action goes right through the axis, so the moment arm is 0, so torque 3 is 0. The torque created by force 3 is 0. So it's just F1 and F2 which contribute. So the sum of the torques is F1R minus F2R over 2, which is what I wrote here. And I factored out the R because it's common to both terms. I get R times F1 minus F2 over 2. Then I just plugged in the numbers, and that gives you the net torque. So 13 is the same setup as 12, so you can do the same thing to find the net. I don't know what's going on here with my boxes. Something's not working right. All right, that's better. Anyhow, 13 is the same setup as 12. So you can use the same equation that we used here to find the net torque. That's where you start. And so it's the same thing. It's the same setup as 12. You can go through 12 again if you don't understand where it came from. If you skip the 13, just go back to 12 for the explanation. So this is the net torque following the same equation that I used for 12. And the net torque is equal to the moment of inertia about the center times the angular acceleration about the center. So the moment of inertia about the center is cmr squared, and so you just divide by cmr squared, and that gives you the angular acceleration about the center. Meaning it's going to cause the disk to spin, right? Because the angular acceleration isn't 0. 13 is just one more step from 14 is just one more step from 13. So you find the net torque as you did in 12. You find alpha as you did in 13. And then what you do is you do one more step. You have to use a constant angular acceleration equation to figure out how many revolutions it makes. So once again, we're asking for a delta theta type thing. We know it starts from rest. We know alpha and we know t. So this is the equation that we use. So you plug in alpha at the time, and that gives you how far it spun in radians, and then you once again convert, like we did a few problems ago, from radians to revolutions, and that gives you how many revolutions it makes. So you should know how to calculate torque when the torque isn't 0, as it is for 12, 13, and 14. You should know how to calculate the angular acceleration like we did in 13. You should know how to plug that into constant angular acceleration equations and do something like we did in 14 for the test as well. Last one is 15, which is a equilibrium case where the thing isn't rotating. So the question is, what's the weight? And we know Fn1, but we don't know Fn2 or the weight, because that's the question, what's the weight? So what you want to do is, this isn't rotating, so the sum of the torques is 0 about any point you choose. So you can choose the axis to be anywhere. So what I did is I chose it to be over Fn2 because I don't know Fn2 either. But if I chose it over Fn2, it gets rid of Fn2, so I don't care about it anymore. And it leaves the torque created by the weight, which is the thing I want to figure out. And it also leaves the torque created by Fn1, which is the thing that I could calculate. So what I did here is I drew the lines of action for F1. And then the line of action, I don't know where my cursor is. The line of action, the moment arm goes from the axis. I drew it a little bit below the axis, but you get the idea, to the line of action here, perpendicular to it. So this is L1 from here to here. It's basically the distance between the supports. So the distance between the supports over here is the whole length of the board minus how far this one is from the left end minus how far this one is from the right end. That gives you L1. And also this force here is causing a clockwise rotation about this axis. So it's negative. Minus Fn1 times L1. And then the torque from the weight is, here's the line of action for the weight. Here's the moment arm from the weight, goes from the axis to the line of action. So it's this line here from here to the middle of the board. So the LW is half the length of the board minus this distance here. It gives you the remaining distance, which is LW. And this weight makes it rotate counterclockwise about this axis. So it's going to be a positive torque. So it's positive W times LW minus Fn1 times L1 is equal to 0, which is what I wrote here. Well, in a different order, but you get the idea. So basically, you can solve for the weight. You add Fn1, F1. It's supposed to be Fn1, but you get the idea. F1, L1 to both sides. Actually, I'll change that because it's maybe slightly confusing, although I don't think it's that confusing. Then we just box the answer first. Then I'm going to change that to Fn1. Anyhow, you add Fn1, L1 to both sides. You divide by LW. You plug in the moment arms, and then you plug in the numbers, and you get the weight. So you should know how to do static equilibrium problems as well, and know that you can choose the axis to be anywhere you want. And that's the the chunk of calculations you'll see on the test for both the multiple choice and the written related to the non-extra credit material. So it can be from collisions, conservation of momentum, average force with momentum, kinetic energy with momentum, elastic collisions, inelastic collisions, constant angular acceleration, rotational kinetic energy, moment of inertia, rolling without slipping, net torque where the torque doesn't sum to 0, and torque where it sums to 0. You need to know all that for the test, but if you do know it well, you should do pretty well on the test. So that's the solution for quiz 8, the last quiz of the semester.